So this story starts about 3 years ago. I had recently obtained my PhD in machine learning and decided I wanted to continue pursuing research on this field, but outside of academia. So what I did is I started my own research institute. I hired an office space. I found a bunch of people who I worked with previously, got some students in, and together we started the Asimov Institute, and we decided we'd only do projects that we were interested in pursuing around the field of deep learning and creativity. And so one of the students at some point, after a couple of months after we started, came up to me and said, why are there so many different types of neural networks nowadays? We have this Cambrian explosion of neural network types. This was 2016, so right in the middle of the deep learning trend. I said to him, well, let's find out. Let's dive into this and let's try to get an overview of all of them. So that's what we did. We talked about the chronology of the networks. We looked up the reference papers. And the end result looked so nice that I suggested to him that he not only make it part of his thesis, but that he would publish it as a blog post on our website. So he did. So this is what the neural network zoo looks like. We decided to name it zoo after the particle zoo. So, but then, of course, the AI edition. And what you can see, it's not entirely chronological. I mean, it's also aesthetically pleasing. So the Kohona network, which was decades old, is right at the bottom. But in general, you can see a sort of a couple of trends from this. And I decided when Terry asked me about giving a talk about neural networks, I decided that I would make a taxonomy of this zoo to discern a bunch of trends. And maybe at the end of the presentation, if there's time left, we can look at projections into the future to see where this interesting field is going. So these are the 5 trends that are part of my classification. Oh, sorry. There's one additional slide. I just received a couple of photos from the Ars Electronica Museum in Linz, Austria, where they made an exhibition about artificial intelligence, and they used our blog post as part of it. So I was very proud of that, so I decided to include it in the presentation. So these are the 5 trends that I want to talk about. They will also give you a nice introduction into the field. So if you don't know why deep learning is called deep learning, or you don't know how neural networks work, or what you can do with them, hopefully by the end of this hour you will know, and you can tell your friends. So these are the 5 things, and I want to start with depth, of course, to explain why deep learning is called deep learning. And as you can see, I've highlighted the networks that have depth. As you can see, and I'll show this with each of the 5 trends, they will gradually, the types of networks will gradually increase over time if you go from the top to the bottom. So let's dive in first. So this is a typical task for a neural network. The challenge here is to automate the classification of chihuahuas and muffins. And even for us humans, this would be a particularly difficult task. But how will we go about and do this? Well, we first start collecting a training set. We label the training set, so we have a human deciding which one is a muffin and which one is a chihuahua. And then we use this training set as input for the neural network. And this is it's a simplified network, but I think this is enough to get the gist of it. So what happens is that the photo of, in this case, the chihuahua, is inserted into the network through a bunch of input neurons that are all connected to an output neuron. The input is multiplied by a weight factor. The weight factor is what varies in a neural network. It's basically what sets the boundaries of what the output will be. And then finally, there's a threshold function at the end. And if the value of this neuron is above a certain threshold, it outputs a dog, and if it's below it, it would output a muffin. And the way these networks learn is through a 2-step process. So first, we go feed-forward. So we forward the data, the picture, into the network and see what the output is. And then we have a feedback process, so often called backpropagation, where we compare the output of the network with the desired output, in this case, dog. If it's correct, that informs the model. If it's incorrect, it also informs the model. And then we change the weight values, the weight vector of the network. And gradually, over time, we hope that the network will be able to discern these two kinds of images. And not only that, we hope that it will generalize over other types of dog images and muffin images. Because, of course, the purpose of this is to also recognize new images and not just images that were present in the data set. Otherwise, we could have used a simple database. So what I'd like to dive into is a little more technical, which is how does a network learn and what can a network learn? And if we consider a network like this, so it's a very simple network, it's called a perceptron with 2 input neurons and 1 output neuron. We can imagine that we would like it to learn the AND gate function. So I made a little table on the top left, which basically said that if one of the 2 neurons, or sorry, if both of the 2 neurons are on, we would like the output neuron to also be on. And if one of them or both of them are off, we would like the output neuron to be off. And the way we can represent this problem is shown on the right. We can map the input values to a 2-dimensional chart. We would like the black dots to be separated from the white dot representing the 1-1 input. And then the challenge for the neural network is to draw a line into this space that linearly separates the zeros from the ones. And in this case, we can see that given a bunch of iterations, if we set the weights correctly, it is able to find an output, a weight setting. And we could do a similar thing for the OR gate. So again, it's only that the output changes. So the desired output now is that if one of the input neurons is set to on, we'd also like the output to be set to on. And the way this can be represented in this case is drawing a line between the 0, 0 coordinate and the other coordinates. Now, and this is back in 1969, Marvin Minsky and Papert showed that there is a theoretical limit to this kind of model, this perceptual model. And this limit is represented or can be represented by the XOR gate, the exclusive OR, which is a function that says I only want the output unit to be 1 if either one of the input units is 1. So if both of them are set to 1, I want the output to be 0. And this can be represented into this feature space on the right. And as you can see, there's no way I can draw a line that separates the zeros from the ones, which proves that this model is unfit to represent this function, which is a theoretical limit. And it's also which caused the first AI winter, which in AI means there's no funding for any research. So it took about 15 years, I think, 20 years, to come up with the solution. And the solution looks like this. What we do is we add an additional layer between the input and the output layer. We call this the hidden layer, because it's not interfacing directly with the input or output. And this way we can, one way of thinking about it is that it's no longer a linear separability problem because it's no longer linear. We can actually have a different function. So the first transformation from the input layer to the hidden layer transforms the feature space, and then we have another transformation which makes it possible again to separate the ones from the zeros as desired. So with this theoretical limit removed, the field of AI spurred a new set of research questions. And what we found out is that this model with one hidden layer is a universal function approximator, meaning that given enough units in the hidden layer, this model could represent any function we would like to train it on. So that's sort of the short history of deep learning. Why deep? Well, because we have hidden layers. And like I said, one hidden layer is enough to represent all potential functions. But there was a different problem now, which is that the performance of these networks was unfeasible. So which basically means that it took way too long to train these models to do anything useful outside of a few very specific tasks. And then it took another couple of decades for neural networks to pick up speed again. The reason that happened is because we saw that we could add additional hidden layers to this network that could speed up the training speed. And that brings us to the second trend in this neural network zoo, which is the rise of specialized models. I highlighted a couple. On the top right, you can see the LSTM, which is a very popular model that's widely used. We see convolutional models, which are with the purple dots, which are used in graphics a lot. The GAN, generative adversarial network, attention network. So these are all fit for particular tasks. And I've highlighted one here, which is a convolutional network. So as you can see, these networks consist of many layers, and in reality, they can consist of many more layers than shown here. And what we can see here is that if we look inside of these neurons, or inside of these networks, we can see that a particular type of activation is triggered in a particular layer. And this is not very much unlike how the visual cortex represents or processes information. So if you look to the bottom right, this is a network trained for facial recognition. In the beginning of the network, the left part, close to the input, we see something that looks like a Gabor filter, so low-level features being recognized, and then midway through the level, we see some mid-level features like noses and eyes and ears, and then finally, all the way to the right is where the facial recognition happens. So this shouldn't be mistaken for the grandmother cell. It doesn't mean that a particular neuron is activated for a particular phase, but what it does mean is that in order to excite a particular neuron maximally, this input is shown to be useful for that. So for instance, the cat neuron there, if we show this network the face of the cat, that neuron is very active. So that's how we know that it's triggered by it. So not only are we now able to train these networks faster because we've added in more depth, more layers, but it also allows for specialization within the network. So some parts of the network are responsible for certain functions. And we can see this growth of network size, network depth, in another example where we have the Boltzmann machines, which are an invention of Jeff Hinton, I think back late 80s. Then Smolensky came about with the restricted Boltzmann machines, which was a much more better performing type of neural network. And very recently, only a decade ago, Jeff Hinton again came up with the invention of stacking these networks on top of each other. So basically, each of these restricted Boltzmann machines would be analyzing the activity in the network below, which led to deep belief networks, a very successful type of network for image recognition in particular. And so what we can do with these specialized networks, in this case we have a convolutional network. For example, we can colorize images. So on the top you see a black and white image which is automatically colored by this network. Now you might wonder, how does a network do this? How does it know that grass should be green and that streets should be gray? Well, I can show you the architecture of this network. And you'll notice that there's one stream of data. Also notice how much of engineering went into this. So this is no longer a general model that automatically fits itself to the task. I mean, we have to set this up exactly in this way in order for it to work. There's one stream of data which does classification. So it knows that in this picture there's a formal garden, there's an arch, there might be a golf course in there. It's not sure. And there's another layer which looks at not the objects but the features of the picture. And then finally there's a colorization network which combines its knowledge of how things should be colored with what's in that picture. And then finally it creates a colorized image. Another specialized type of network, it's very recent, only a couple of years old, is the attention mechanism inside neural networks. So what we do here is and you see that on the green dot on the bottom right. This network is responsible for figuring out which part of the picture are relevant for which task. So in this case, it's a little bit blurry, but what it's saying on the top left is a woman is throwing a frisbee in the park. The frisbee is underlined, so we'd like the network to pay close attention to the frisbee. And you can see in the image to the right of it that the frisbee is highlighted. So we can actually steer the attention of the network in a particular direction just by learning what these objects mean, these word objects mean in a pictorial form. So I'd like to draw a sort of overarching conclusion of these specialized network types. In one way, they are an improvement. They allow us to learn certain tasks that we are after, like the automated image colorization, that weren't possible before. In another way, they're also very limiting, because by engineering these networks and setting up in this very particular way, we constrain the space of what these networks can become. We steer them in a particular direction. And so these design network architectures, we decide for them what they will learn and what can be learned, and which is basically a reduction of the latent space of the potential constraints of what can be learned. So the latent space is the space, the internal representation of the network in the hidden layers. This representation is reduced for this particular task. Another downside of using these specialized networks is that we move away from our biological inspiration. So the network I showed previously, even though there's some parallels with the visual cortex, if we want to improve on this network, we can no longer look at the brain as an example. So it's in one way, it's very helpful to keep the models general and not too much tailored or engineered in order to make fundamental progress in our field. Right. Then on to the third type of, the third classification that we can make for these networks, that is scale. So many of these networks operate much better in a larger scale. And scale is actually what's responsible, you could say, for so much of the success recently in deep learning. If we look at which times these networks came about, many of them came about before the year 2000, but just we weren't able to feasibly train them because we were lacking the scale. And it's only since the rise of the internet, the rise of GPUs, cheap processing power, when they've come to full fruition. So if we look at these exponential graphs, we can see that the data has been growing, of course, due to the rise of the internet, so there's much more to train from. The processing power has increased dramatically, storage costs have dropped, so these are all great conditions for these type of networks to learn from. What's not shown in this picture is that neural networks can also be very easily distributed over multiple systems because they're a very general model. So I'd like to quote two famous researchers in this field. The first is Ilya Sutskever, who is responsible partially responsible for ImageNet, which in 2012 won an image recognition competition. And so he was also one of the big founders of this revolution. And what he says is, what are the key factors that have enabled recent advancements in deep learning? Sufficiently fast computers, the availability of sufficiently large, high-quality labeled data sets, and algorithms, techniques, and skills for training these large, deep networks. What can be added to it, or what can be read in this sufficiently fast computers, is also the rise of the GPU, graphical processing unit, which was originally invented for gaming to make the triangulation of polygons, the polygon generation, to make that a lot faster. But it turned out that you could represent these networks as matrices, and that GPUs are very fast in calculating with matrices. So GPUs are now used all over the place to speed up the training process of these neural networks. And the second quote I picked out is from Rodney Brooks, who also mentions maybe a bit of a downside of skill, or maybe points out another upper limit of what machine learning can do, which is that machine learning is very brittle, and it requires lots of preparation by human researchers or engineers, special purpose coding, special purpose sets of training data, and a custom learning structure for each new problem domain. So that's not nothing. That's a lot of things that you actually need in order to get a machine learning system going. So sometimes we machine learners talk about these magical neural nets and this magical deep learning, which somehow comes up with all these answers that we're looking for. But there's a lot of hidden work behind it. And this hidden work also points out the limitations of what we can actually do. So to give you an example again, here's the Chihuahua again. What's actually happening is, of course, we still need to find a way to input this picture in the neural network. I mean, neural networks don't do well with pictures, they need data. So we need to transform this, this picture. And now I, as an engineer, would have to decide which features are relevant for the problem to solve. And I know, it's also sort of a pragmatic argument, I know that I'm interested in separating this picture from, this dog from muffins. And so I might say, well, the color of the image is not important. So my first transformation, oh, I see it's not working well. I need to go here. My first transformation is to turn the image into grayscale. And then I might say, well, now I want to rasterize this picture. So I can cut it up into parts. I have to make a decision on how big the raster is, how many parts I need, etc. And then I can finally feed this information into the input layer of the neural network. But as I go along, as I make these decisions, I've also constrained which features the network can learn from. So there's some implicit assumptions about the learning task that I, as an engineer, have done, which might be relevant. So maybe the network is indeed finding color useful for discerning between the dog and the muffin, but now I've removed that option for it. So in feature engineering, which is a necessity, we also find a constraint of the feature space. We are forced to do so because simply the training time is limited. So we have to design some of these features. But like I said, that requires assumptions on what features are relevant. And that, again, puts the burden on the engineer rather than on the machine learning network. And the expectations of the engineer create a sort of an upper limit on what can be learned. And this is problematic in some way. So like I said, we started the Asimov Institute with the idea of investigating deep learning and creativity. From a creativity perspective, what we'd like the network to do is actually explore an almost unbounded space of possibilities. But as we come up with these learning tasks, and we as humans decide which features are relevant and which are not relevant, it puts us in a difficult position. Because either the solution that the network is looking for is within the search space that we devise for it, which means that the computer itself can't think outside the box, or the solution lies outside of the box, but then we as engineers have already removed the feature, so there's no potential way even for the system to come up with a solution that it might be looking for. So in order to get to full creativity or transformational creativity, we would like to have a system that is inside some kind of box and then gets out of it. And so as a thought experiment about this idea, this box paradox, I'd like to do an experiment with you. I'd like to ask you to think about this riddle, the answer to this riddle, but as you're thinking, so this is one step up, to think about your thinking process. So what process are you going through while you're solving this riddle? I'll give you a minute to have a look at it. So if you found the answer, or think you found the answer to this riddle, could you raise your hand? See. Yes. You say? You knew the answer already. Yeah. Then it's easy. Yeah. Maybe I'll ask a person in the back. Sorry, I couldn't. I saw you. Yeah.
Just the middle switch.
The middle switch.
Turn on the middle switch.
And how does that solve the riddle?
I would think it would relate to the order of the lights, and I could compare the sequence of the switches to the sequence of lights.
Aha, but it's not necessarily sequenced. Maybe I should have told that from the start. Yeah. Another one? Yes?
So I would turn one on for a while, and then turn it off, and just leave the other one off. And I would walk in, and the warm one would be the one that I turned off, and the other one would be off.
Yes, it's very good. Let me maybe, yes. Absolutely. So the answer is here to put one switch on for a while, then turn it back off again, and then do a second switch on, and then walk into the other room. And that means that one of the light bulbs will be off and cold, one of the light bulbs will be off and warm, and one of them will be on. And that's how you relate the light bulbs with the switches. So could I ask you something else? Could you tell us how you got to that answer? Right, yeah. You're thinking outside the box. Because the initial box which we're all stuck in the beginning is the idea that there's a combinatorial solution to this problem. So if there's any combination of switches that I can do to get to the answer, that's what we sort of naturally first explore. But we soon find out that there's no answer to this question. So what we humans are capable of is to actually transform our own search space, because we know there's probably an answer, otherwise I wouldn't have asked you this riddle. We transform our search space, and in this case, we include heat into the equation. We say, well, what can lamps do? Well, they give off light, but they also give off heat. So this is a transformation of the search space. And if you want to have a creative system, this is a very nice property to have. So it's thinking outside the box, but always within the bigger box that exists, of course. So the network topology and the amount of neurons always places an upper limit on what the network can represent. But inside this box, it can look for a particular answer, just as we were looking for a combinatorial explanation of the switches, and then shift to a different style or a different type of answer. But in order for the network to have this kind of behavior, to be able to think outside the box, first we need scale. And as we just said, as we just seen, these deep neural networks, given everything that's happened over the past decades, they now have sufficient scale to actually start surprising us. So what I'm going to show you now is a video clip from DeepMind, a London-based company which is acquired by Google. And what they will do is they will play a game. And what's interesting to notice here is that the network that is playing this game, it doesn't get any features of the game. It gets the pixels as input. So it sees exactly what we are seeing. So there was no feature engineering done. And on the output side, it is able to control a joystick, so left and right with Atari Breakout. And here we see the agent playing after a bit of training. We see it sometimes move towards the ball, but it also fails a lot of times. And so the programmers hadn't defined the concept of ball and stick. They only showed it the pixels, and they showed it the score. So they had to have a concept of value. So in this case, the score was given. And then after 2 hours of training, we can see that the network has learned to play quite well. It fails sometimes, but not very often. I would say at this point it's at human capacity or probably slightly better, depending on how often you play games. And then something interesting happens. The researchers continue to let the network train. So nothing unusual yet. And then we see it suddenly came up with this solution, which initially was outside of its gaming style, you might say, outside of his range of what it would normally do, even though it was in the realm of possibilities, of course. It would control the joystick in the same way that it does now. But because we gave it the score, and the score was dependent on the time, it kept searching for a more optimal solution, and ultimately it found a different playing style, one that surprises us. So scale means that this feature engineering, which was always part of machine learning, now to some respects has been surpassed, and that these networks can also surpass our expectations of it. Then a fourth trend in deep learning that I'd like to point out is the concept of unsupervised learning. So typically, if we think about machine learning, and also in the example I showed previously of the dog and the muffin, we have labeled data sets. So we tell the network in the training set, this is a dog, this is a muffin. That's how you distinguish the two. With unsupervised learning, there's no label. So we just feed it the data, and then we let the network learn, which means that it can't really do anything that we would like it to do, you'd say. It just represents a latent space based on the characteristics of the input. But still, there's ways you can use that, as I'm about to show you. So the types of networks that we see here are the autoencoder, the variational autoencoder, some Hopfield network, the deep belief network that I mentioned, the generative adversarial network, and the Cohoner network, which are unsupervised. So before I show you some examples of unsupervised learning, I'd like to dive into the concept of latent space with a short anecdote by the company Netflix. So what they used to do is they would, of course, give you recommendations. And the way they would do that is they define a number of dimensions on which to classify viewers and users. So they would say, well, are you a man or a woman? Are you an introvert or are you an extrovert? They'd had about, I don't know, I think about 20 of those dimensions. And the point on that multidimensional space determined who you are for them. And then if there were people close to you in this multidimensional space, they probably had the same preferences, they assumed. And so you'd get the same type of recommendations. And that's generally how recommendation systems work. A couple of years back, Netflix decided to reverse the process. They decided to look at all the data they had and then determine which dimensions were the most telling for recommendations. So instead of engineering the dimensions, they let the system figure out which dimensions separate out the users the most and then use that for their recommendations. And the network came up with 51 dimensions. For some of these dimensions, it was clear what was meant. So they saw a clear separation between people on the left side of the dimension and the people on the right side of the dimension. But for about 30 of those dimensions, they had no idea what it meant. So they saw, you could draw a line of this dimension. They saw people all over the place. There wasn't a way you could distinguish between those people, but for the network that had learned it, it made a lot of difference whether you were on the left side or the right side, and it would base those recommendations on it. So this gives you an idea of not only the usefulness of this latent space, this representational space that networks use, but also of the black box quality of it, which simply doesn't mean anything to us. But we can use it in interesting ways. So I've made a simple representation of latent space. So in this case, we have 3 axes. In reality, there's probably a lot more. And what neural networks do when they have these hidden layers is they cluster the observed data together in latent space. So that means that there's a cluster in this image recognition for cats, where all the cats are grouped together. And then we can use that if you want to recognize cats, we know that's the cats cluster. But what we can also do is sample from this space. So we can actually say, well, I'd like now to get a type of input which could also be in this space, which I haven't seen before. So that's how you get these generative images. I think I see a question over there. Is that correct?
How in unsupervised learning you tell the network what it's supposed to do? What is the task? How you are doing it?
Yes. Depends on the network. So the question was, how do you tell the network what to do? It depends a bit on the network. If I have time, I can show you one example of the generative adversarial network, how it learns. But in this case, we can first train the network on recognizing labeled images. So we create the model by having these labeled as cats to put them together. But once we have the model, we take it out, and then we can use the network to generate. So in this case, labeled data was used to first create the latent space, and then we use the model without any labels to generate new examples. Yeah, I can show you an example later where there's no labeling, but this is, So these are cats that don't exist. When I made this slide, I realized that for me, this picture looks a bit dated. I think this morning with Tristan Harris's talk, we also saw examples of much more high-resolution images. So this is research from 2017, I think, these cats. And this is what it looks like now. So if you go to the website, thispersondoesn'texist.com, you can just refresh the page, and you get faces of people who don't exist. So this is another one. Now, if you look at the face, it's almost impossible to see that it's a generated face. If you look at the background, though, you see it has some weird artifacts. That's because the network wasn't trained to make realistic backgrounds. It was trained to make realistic faces. So it's interesting to just refresh that page and do some artifact spotting. We can do a similar thing. It's a little bit different process. We could do a similar thing for paintings. So this Rembrandt, for example, was never painted by Rembrandt. It was generated. Also, there was some human work in creating this, but it was generated by a network who analyzed previous paintings from Rembrandt. We can do all kinds of things, not just labeled data, but also descriptions of data. So we can have a sentence like, this bird has a black head, a pointy orange beak, and yellow body. And then we can even use a marker to show where it needs to generate this image inside the picture, and then the network starts generating it. So it's a reversal of the normal task where we load in an image and then generate a description of it, basically. Some other, I would say, funny explorations that we can do in latent space. These representations are numerical, so they are vectors in a multidimensional space, which also means that we can average them. So we could have a flower somewhere, we could have a dog, and then we could use these two vectors to create an average and say, well, what does a flower dog look like? And it turns out it looks like this. Similarly, we can do another nice example is a geyser and a dog, which turns out looks like this. And then finally, if you ever wondered what a cappuccino dog looks like, it looks like this. So as you can see, there's lots of creative value in these kind of networks and these tools. Another famous example is not so much to average out these numerical vectors, but to use the style of one image, which is a particular features of this latent space with the contents of another picture. So you have the style photo, you have a content photo, and then you can apply the style of one picture to the content from another picture and get a third picture. So this is all automatic. There was no human work done in transferring the first two pictures to the third picture. More famous example is applying art styles, so the contents of the Mona Lisa with a different style. And this is, I'm inclined to say it's a bit sad. This is a Dutch project. It's called Loving Vincent. It's a movie that came out recently, I think about 2 years ago. The idea is that a group of painters have undertaken a 10-year project to make the first painted movie ever. So it's an entire full-length feature film where every frame has been painted by hand. And imagine what this means, that by the time that the movie came out, we had this style transfer.
And there was a letter out there that you had
I'm not going to show you the full-length feature film, but we had this style transfer where we could actually apply the style of a painting, not just to images, but also to movies. So here we have Ice Age, and we have Van Gogh's Starry Night. This is still... we have to get the variables more constant, and then we can get things like this. And again, there's no human work involved after the model has been trained. So there's endless opportunities of playing around with different pieces of content and different styles. All right. Should probably get a move on. Yeah, I'm quickly going to also describe this project to us. So this is a different project that we did at the Asimov Institute. We had a fashion designer involved. We had some interesting discussions about her creative process, and she said the fashion industry is not creative anymore. So what we said is, well, what if we try to predict next year's fashion? If we succeed in predicting it with these networks, that basically means that the fashion industry is as creative as a computer, and that might create some turmoil in the industry and hopefully get them to think about their creative process. So what we did is we got some images from a website. This is a great data set because the images are a lot alike. The picture is taken from the same angle. We had 500 of them. And then we trained just one processor, 20 hours. We trained a generative adversarial network on this. And the way the network like this works is that we have this database of 500 images. Then we have a generator, which randomly produces images. It's a bit more than random. It uses some intelligence, but let's for the sake of this argument, assume it's randomness. And then there's a discriminator neural network, which is given the tasks to discern which image has been generated and which is real. Now, as you can imagine, as a generator network produces better looking images, then the discriminator network is having a hard time figuring out which one is real. So the success rate of the discriminator network can be used as an error signal to feed back into the generator, so the generator knows it's doing well. It's a bit like the Turing test, but then with one applicant. So this model has been used. We use this to generate new images based on the data set. This is a selection of those images. As you can see, it's not very high resolution, but then you probably need a lot more computer power to do that. We also didn't think that this would be the end result. Nobody's going to wear this. So what we did is we had a project or an approach of hybrid creativity, or augmented creativity, where the fashion designer would sort of use this as a tool, go back and forth with it, generate some images, do some designs. So like I said, it's sort of exploring the creative space, going in and out of ideas. And sometimes it's the computer's move, and sometimes it's the artist's move. And then this is the exposition. I think last year she finished her collection, and these are some of the results of that project. She called it Deep. It's the name of the collection. All right. So on to the final trend in deep learning, and then I'll have some time, a couple of minutes, I hope, to give you some projections out of this. So dynamical models. They've been around for a while. I would say they've increased in popularity, but the reason I put them on here is because they have some very interesting properties, particularly moving forward in the field. So the networks I've shown you thus far can be seen as filters, or they forward information from input to output. But as the brain works, we could also have recurrent connections within these networks. But it introduces a lot of complexity. For instance, it introduces time into the network. So if we want to have a learning algorithm for these kind of networks, we have to basically unfold the recurrent connections over time. So as you can see in the top right, we have a very simple network with one recurrent connection, but if you want to train this network, we have to pretend it's a very deep network in order for the backpropagation to work. Another problem that we see is that so-called vanishing gradient problem, so that when certain activity over time is being recycled in the recurrent connections, it slowly vanishes, which means that over time some information might be lost, and the most actual information is used more than the older information. An interesting property that we see here is that there can be activity without a stimulus. So all the linear networks are stimulus-driven, meaning there's only activity when something is shown, whereas in these kind of networks, you could imagine that the recurrent connections would be continually active, and also that if I show the same input twice, that I would get a different end result, a different output, which is also more biologically accurate than a normal computer or a feedforward network. A very prominent or interesting example, it's not prominent, it's not used much, but an interesting example of recurrent networks are so-called liquid state machines. What researchers here try to do is to represent the input patterns as dynamical patterns. So what you could see on the right is they actually built a liquid reservoir. They would use these plotters for different input signals to create waves on the water. And then they had a visual recognition network that looks at the waves over time and then tries to learn what type of input was given and how to correlate the two. But you can imagine that there's a timing element that plays a role. So the moment when a certain plotter hits the water creates a different kind of ripple, and when you take the picture, it also affects what you see. So there's a neural network variant of this, which is but one big neuron soup with output neurons looking at them, but there's also a physical model for that, which is called reservoir computing. And one way to think about this, so this is a dynamical representation of this latent space that we've seen previously. Another example of dynamical neural networks is predictive coding. Also recent, I think this is about 2 years old, where we don't use labeled data, but we use the input data for t+1 as the error signal. So basically what the network tries to do is to predict what it's going to see next. And then the goal of the network is to minimize the surprise or maximize the prediction accuracy of what's going to see next. So there's no labeling necessary here, but the network can learn just from observing the world around it and try to predict it. And what you can see here is, so on the top you see the actual camera footage from, in this case, this is a part of self-driving car research. And then on the bottom you see the predicted image as predicted by the BredNet. Now if I show you 5-step predictions ahead, what you can see nicely on the top again, so there's the predictions. Predictions become much more blurry over time. So one time step ahead, we can have a pretty accurate image of what it would look like, but 5 steps ahead, it becomes much more blurry. What you can also see is that the network learns particular types of behavior of the world around it. So if something moves forward towards it, it becomes bigger. The way shadows move towards it, it learns these kind of patterns out of the world. And one way to think about using this is to just have a camera, for instance, in your factory floor, hanging on top of it. It just observes the space, and this can be used for accident prevention. So as soon as something happens that the network can't predict, so it sees something irregular, it might raise an alarm. And it could mean that there's a smoke signal, it could mean there's nothing wrong, but the absence of predictability might indicate that there's something unexpected that's going to happen. And of course, we can use the same type of technology for monitoring large groups of crowds and to catch incidents before they actually occur. All right. So how much time do I have left, more or less? Yeah, okay. I don't think this will take long. I just wanted to present you with something beyond what I've shown you, so a bit of a synthesis or maybe some projections. I'm not going to use the word prediction because I don't think this field can be predicted, but we can extrapolate from what we've seen. And there's 4 themes that I think we can extrapolate towards. So the first is biological inspiration. And I think we've covered parts of this. So first we've seen that the neuron, the artificial neuron, of course, it's inspired by biology. It's no way near what the actual neuron works like. It's actually closer to a transistor than to an actual neuron. But we might say that the birth of neural networks was inspired by the brain. Then the idea of depth, the idea of dynamics within the network, recurrent connections, attention, again, something that was borrowed from physiology into a machine learning field. And unsupervised learning, of course, is also biologically accurate. We do have something like instructed learning, but most of our learning process is not done in a supervised way. It's actually just by us observing the world and trying to predicting what's going to happen next. And then I've plotted a line there for the future. So things that we could see happening over time is sparse networks. So network size actually decreasing and requiring less processing power. Because as we saw, much of this revolution has been caused by an increase of scale. And there's limits to that scale. And one limit is the energy consumption of these networks. And as we see more applications coming, we also see that the energy consumption and the cost and also the impact on climate has exponentially increased. And one way to limit this is actually to come up with smarter and more elegant and more efficient networks that use less units, less processing power. Another observation or extrapolation is the sparsity of data. So with learning with less data, that's a challenge that's being picked up right now. I can show you quickly an example of this. So what it's doing here is not the most interesting thing.
That can learn realistic talking head models.
What it's doing is it's picking up this facial video, and then it has a bunch of pictures from someone else. It projects this onto this facial video. I'm sure many of you have seen this sort of deepfake idea. What's special about it is that it's only seen 8 images of this person. So even then, it's able to produce a video based on these 8 images.
Effective.
And what these researchers show is that 8 images actually, they can do it with 1. So if you show 1 image, then a network can project onto it these facial dynamics.
Applying the system to
and so that's of course very interesting, because that means that you can create these living portraits. I was surprised by it. I mean, this came out last week, I think. I decided to put it into the presentation last minute. because I think it's just a neat example.
With a certain degree of success, we can even apply the model to paintings, despite the large domain gap between paintings and YouTube videos. Here, we can see that in some cases, the model might be very sensitive to the geometry of the landmarks. Driving Mona Lisa with landmarks from 3 different people.
So I've been working in this field for a while, but I still get surprised almost on a weekly basis by this kind of results. All right. Moving on to the second projection into the future. We're constantly pushing the boundaries of human ingenuity. So if we start with algorithm design, programming, we see that machine learning basically pushes this boundary. So if we try to write a filter that distinguishes dogs from muffins, that would be very difficult to program, because we can of course try to recognize the features in there, etc. But using machine learning just allows us to do this much better than we could ever do with a piece of software written by a single person or a team. And we see a similar move where we push the boundaries with deep learning, where the model and the feature engineering is suddenly no longer a human task, but it's actually pushed towards the network. For model selection, so which of the neural zoo models we need to select, there are tools coming up like AutoML, where the system just tries out different models and see which one predicts best. So I no longer have to choose which model I want to use. The software can figure it out, given it has enough processing power. The data preparation, which Rodney Book showed, is also a human task. Well, with all this unstructured data, this camera data that comes in with this skill, we might no longer need to prepare a lot of data. We can just let the network, the intelligence, stand in the world and observe the world around it. And with this unsupervised learning, even the task definition doesn't have to be clear. So we can just tell it, if you can't predict anymore what's going to happen, raise an alarm. Yeah. And so what we're moving towards is black box systems. What we're also seeing is that we're retracting from the design of these systems. And that brings us into all kinds of common sense problems and ethical problems, because the human engineer is no longer directly in control of the design and the process. And then finally, this is my last slide, I'll end with this. I want to point out some interesting opportunities for future research. So what we've seen is that the history of deep learning is also a history of dimensions of depth. So as we move from the perceptron, which has no latent space, to a single hidden layer network, which is representational capacities, but no feasibility capacities, we move to a multiple hidden layer network, which has feasible training time, but some vanishing gradients. And finally, we have these stacked networks, these specialized networks. What we see is that there are statical models of this, but there's also dynamical models of this. So the recurrent network is a dynamical model of the hidden layer network. And on the bottom right, I identify a potentially new type of network where we have a dynamical model of network hierarchy, which is a dynamical model of these stacked networks that have proven us so much. All right, I wanted to end with some ethical consequences, but I'll leave this for another talk. So I'd like to thank you for your attention.